I'm Ethan Deyle. I don't know about everybody else, but when I hear climate change and infectious disease, the first thing I think about is causal inference. Am I the only one, maybe, in front of the microphone? They say when you have a hammer, everything looks like a nail. I guess I have a similar case where when you have a data science approach to understanding coupling in complex nonlinear systems that don't fit traditional paradigms of reductionist causality, everything looks like a nonlinear system producing time series data. Like dengue. So this is a study, this is not my day job, but this is something I been involved this kind of work a few times. This time on invitation from a graduate student in Aaron Mordecai's lab at Stanford who was just visiting. So dengue fever, one of these vector-borne diseases, humans are infected by infected mosquitoes. And dengue is generally regarded as being a seasonal epidemic. And the timing is generally associated with a peak in cases during or after the rainy season. But there's actually many different mechanisms that we can put forward or even measure in laboratories that can mediate the relationship between weather and the actual human caseload. So for example, temperature can affect the mosquito population dynamics. They're exotherms, so the hotter it is, the faster they grow to a point. Same thing for the pathogen itself. And also the temperature can modulate the interaction between humans and mosquitoes. For example, changing the bite rate. When it comes to rainfall, we also expect rainfall might matter because mosquitoes need standing water to reproduce. The story might be a bit complex though, because actually in San Juan, Puerto Rico, where we were focusing the study, humans collect standing water in open containers in the anticipation of drought. And so actually low rainfall may be behind some outbreaks of dengue. A lot of complexity, and is that the, nope. Another thing to remember is that these things don't act independently. These different mechanisms are not separate, but they're integrated through the entwined ecology of the system. And one really obvious thing is that a pandemic can't happen if there's no susceptible humans. So if a dengue epidemic has recently spread through, there's going to be a low level of susceptibility. And so no matter what the temperature is, no matter what precipitation there is, cases are going to stay low. What do the data actually say? Well, when I talk to the data, they say that they need a nonlinear time series approach to really understand their causal interactions. If we just look with a static correlation, if we just try to match the level of cases to the amount of rainfall, we see almost no evidence of interaction. But that's misleading in a case with coupled nonlinear dynamics. When we look instead to see if the driver's affecting change over time, subtly different, but requires different mathematics, we can reveal a lot richer picture underneath. So the lack of correlation really belying a deeper relationship that we can then pull together in a nonlinear model and make quite good forecasts. Of course, that's not what I do in my day job. My day job, I'm usually thinking about ecosystem-based management instead of public health. But many of the same methods and many of the same flavors of questions arise. So right now, what's in front of me, thinking about the effects of fishing or temperature changes on the resilience of coupled communities in reefs, fish and reef communities. So that's a whole nother talk that I'll give some other time, hopefully. Thank you.